Hello everyone, welcome to a long-awaited video for the MCAT. This is our review of MCAT lab techniques. I'd like to start by saying that I did not create this document. This document has been circulated many times through many circles and many subreddits and many messages and many emails. This is the guide to the MCAT lab techniques by I Want a High MCAT Score. I don't know who this person is or how long ago they took the MCAT, but this guide is absolutely phenomenal. And it is what we will be using and taking from in order to learn about lab techniques. Now, if you like the content that I produce, please consider supporting the channel by looking down below for the Buy Me a Coffee page, the Patreon, and my Venmo, of course. And 50% of everything that we raise from the channel will be donated to Doctors Without Borders. Please also consider joining the WhatsApp chat and joining our email list so that you get all of the updates associated with this channel and everything that I do. And I hope that you guys are having a great time studying, and I hope that you're studying very hard. Thank you so much, and let's get right into it. So, lab techniques. The thing about lab techniques is that sometimes they're just really easy points for you to get on the MCAT. Sometimes they'll just ask you straight up a question about lab techniques. Sometimes the lab techniques are going to be incorporated into a passage where they're going to show you the results of a gel, or they're going to show you something from an NMR, or they're going to show you something from a mass spec, and you're going to have to interpret it, right? So let's start with gel electrophoresis, right? And this is basically just going to be us walking through the document and talking about it and looking through everything holistically. So macromolecules, right, large molecules of interest are placed in lanes of a gel. For proteins and small molecules, it will be polyacrylamide. And for larger molecules of DNA, the gel will be agarose, right? An electrical charge is placed across the gel. So at the top over here, we have a negative charge. And at the bottom over here, we have a positive charge, right? There's a positively charged anode and a negatively charged cathode, right? If you guys remember from the electrochem lecture, you know that the anode, we have anox and we have red cat. So reduction happens in the cathode and oxidation happens in the anode, right? Now, here's the thing, right? Here's the thing. The cathode, the reduction is happening. What do you need in order for reduction to happen? What do you need in order for reduction to happen? You need electrons, right? So that's the reason the cathode is negative. And the anode is positive because it's losing those electrons to give over to the cathode. So what I want you to remember whenever you're looking at electrochem is that the anode is giving electrons to the cathode, right? Okay. Very good. So keep in mind, since the voltage source is applied to gel electrophoresis, follows the same principles as an electrolytic cell, like we said, right? So there's an electrolytic cell, right? Where what? We have an outside source. We're plugging in something and we're running a charge through it, right? Okay. Because of the resistance of the gel, larger molecules will have a harder time moving, and thus the molecules will be separated by size, right? Okay. So there's two things that are separating the molecules here. So molecules will be separated by size, and negative molecules will be attracted more towards the bottom, right? Okay, so if you look at the gel, the way that the gel's made up, you can see it's tangly and twisty all over here, right? So the larger molecules are going to get caught in those tangles, so they're not going to move as far, right? And then these molecules, the smaller ones, are going to move further. But one more thing is that the negatively charged small molecules are going to move the furthest, the positively charged small molecules less, because the positively charged are going to be attracted towards the negative terminal up here. So if you see something that travels further through a gel, there's one of two things that can be true. Number one is that it's small, and number two is that it's a negative. Does that make sense? Very good. Okay, cool. The gel can then be stained for visualization using Kumasi blue dye. It's carcinogenic. Don't breathe it in. A lane will be loaded with a collection of molecules of a known size called a ladder, which can be used to determine the size of the molecules being ran. So here's what you're going to see on the test, right? They're going to give you this little sheet. And on the left, they're going to have this, 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 and this. And here it's going to say 10 and 20 and 30 and 40, right? And this is your ladder. This is your ladder. This is a known molecule with a weight of 10. This is a known molecule with a weight of 20. This is a known molecule with a weight of 30. This is a known molecule with a weight of 40, right? Does that make sense? So if you have leg A, or lane A and lane B, and lane A has something here and something here, and lane B has something here and something here, you can easily figure out the weight of these molecules using the ladder. Does that make sense? Very good. And there are several different applications of gel electrophoresis. So let's take a moment and take a look at these applications. Sorry. So, native PAGE. What is PAGE? Polyacrylamide gel electrophoresis. Smaller molecules elute first. Yes, that was the whole point of what we said. Right? Guys, have you ever ran a gel and then gripped the grippy, squishy agar? I have, actually. Native PAGE is a polyacrylamide gel electrophoresis for proteins that occurs under non-denaturing conditions, right? The method will separate proteins by size while retaining their structure. Okay, so let's say, look. Everyone look. Everyone look over here, okay? Let's say that there's a protein that's folded like this. And it weighs 40 kilodaltons. I don't know if that's actually like something that, you know, it would weigh. And let's say there's a protein that's folded like this. And it also weighs 40 kilodaltons. Which of them is going to move quicker through the gel? In a native PAGE. Native. A or B, which one's going to move quicker? B, why? Small ting. Yeah, it's more dense. Very good. It's smaller, so it's going to move faster. SDS-PAGE, SDS standing for sodium dodecyl sulfate, right? SDS-PAGE is a polyacrylamide gel electrophoresis method for proteins that occurs under denaturing conditions, right? So denaturing conditions to separate by mass, okay? So look at this. You could have a really tightly wound protein that's like 60 whatever units you want to call it, and you'd have this, which is 50. And this might move faster initially, right? But if we denature both of them using sodium dodecyl sulfate, then the 60 is going to look like this, and the 50 is going to look like this. And now all of a sudden, this is going to move faster because we've denatured the both of them. Does that make sense? Yes? Very good. Awesome. I like that. I like when things make sense. Okay. Negatively charged sodium dodecyl sulfate is attached to the added to the solution of proteins, denatures the proteins, and binds one SDS for every 2 amino acids, giving all proteins the same charge to mass ratio. Since all proteins have the same charge to mass ratio, they are separated solely on mass, with the smallest proteins found toward the bottom of the gel. Right? SDS will only interrupt non-covalent bonds. If disulfide bridges are present in the protein, they will not be broken. This is important for the next thing. This is useful when analyzing proteins with multiple subunits. Okay? Yes? So let's say that you have hemoglobin. How many subunits does hemoglobin have? 4. What are the names of the 4 subunits? There's 2 of one, there's 2 of another. 2 alpha, 2 beta, right? 2 alpha, 2 beta. Let's say that you did a native gel, a native PAGE with hemoglobin. You would see 1 spike like this. Let's say that you did a SDS PAGE of hemoglobin. How many spikes would you see? How many blots? 2. Why not 4? You fell for the trick. Why not 4? Because the alpha is the same weight as the other alpha, and the beta is the same weight as the other beta. So let's say, and I'm not saying this is true, let's say that the alpha is larger, right? The alpha is going to be here, and the beta is going to be here. But since these are the same weight, you're going to see them stacked on top of one another. And the beta is going to move further because it's lighter. Does that make sense? So, this is the native PAGE of a hemoglobin. This is the SDS PAGE of hemoglobin. Understood? Anyone confused? Because if you're confused now, I can't move on. Okay. Next, reducing SDS-PAGE. Oh, hold on. One more time. Okay. Native. Okay. I'm actually just going to do it like this. Alpha, beta, alpha, beta. And they're connected, right? I run this whole thing through a gel without denaturing them, without putting sodium dodecyl sulfate, right? It comes out as one heavy thing. Okay? Then I add SDS, which gives you an alpha, and a beta, and they're all disconnected, right? They're all disconnected. Okay? When I run the gel again, the alpha is going to show up here and the beta is going to show up here. But there's two alphas. However, they weigh the same amount, so you can't tell the difference between them. So this is what the SDS is going to look like. This is what the native is going to look like. Does that make sense? Thicker bands, yes. If there's two of them, there's going to be a thicker band than if there's one of them. So the band is going to be nice and thick. The band's going to be nice and thick. Make sense? Cool. Reducing SDS-PAGE. This is why I said the end of the last one was important. If disulfide bridges are present in the protein, they will not be broken. A disulfide bridge is what? What's a disulfide bridge? Well, let's say that I have a cysteine molecule. I then add another cysteine molecule. Anyone who hasn't studied biochem yet is shitting their pants right now. I oxidize this thing. Right? I oxidize it. It turns into something that looks like this. That's a disulfide bond. Make sense? Okay. So a reducing SDS-PAGE, right, is like an SDS-PAGE, but with the addition of a reducing agent like beta-mercaptoethanol, which will reduce disulfide bridges and result in a completely denatured protein. Okay. Pop quiz. Ready? Here is the native page of a protein. 2010. Actually, 10, 20, 30, 40. All right. Okay. Here is the SDS-PAGE. 40, 30, 20, 10. All right. Here is the reducing page. Reducing SDS-PAGE. 10, 20, 30, 40. Okay? Tell me a fact about this protein. Natives 40. SDS is still 40. So when we denatured it, nothing happened. But then we added a reducing agent and it dropped to 10. It's the same protein. A lot of people are saying there's 4 subunits. Very good. And each of those 4 subunits weighs 10 kilodaltons. Very good. And they're connected by what? Here's what we learned just from these 3, right? It's a 40 kilodalton protein. It has 4 subunits, each of which are 10 kilodaltons, and all 4 of the subunits are connected by disulfide bonds. Very good. Does that make sense? Cool. So we would call this a homotetramer. A homotetramer. Homo meaning the same, and tetramer meaning 4 pieces. 4 pieces making the same thing. Can you confirm if the band will be thick at 10? It should be, because there's quadruple the amount of stuff. Does that make sense? Okay, so let's change this a little bit. Let's get rid of all this. Native's still going to look like that. Yo, Muhammad Assalamualaikum. He's back. My boy is back. Love this guy, man. I miss you too, bro. I was waiting for this guy to get in chat. 12:30 in the morning, he pulls up. Oh. I was waiting for this man to pull up. Yo, the love that I have for this guy. Oh, I was talking about it the other day. I don't really know why they hate each other. You must be new here. All right. Guys, look at this. Look at this. Ready? There's the SDS, right? So let's answer some questions just by looking at the native and then the SDS as well. So now we know that there's 2 subunits and they're linked what? Covalently or non-covalently? Non-covalently, because we're able to get between them using the SDS, right? But then watch this. Here's your band at 10, and here's a thicker band at what? At what? 15. So why'd the band get thick at 15? What's going on? So let's call this the alpha subunit. And let's call this the beta subunit. Well, what's 15 plus 15? 15 plus 15 is 30. So we're going to say that the alpha subunit is actually made up of 2 covalently linked 15 kilodalton subunits. And then that alpha adds to a 10 kilodalton beta. That alpha in and of itself is a homodimer. A homodimer of 15 kilodalton subunits, and it adds to a 10 kilodalton beta unit in order to make the final protein. Do you see how useful all this is? It's incredible. It's incredible how much information you can squeeze out of this if you truly understand it. And when you guys see it, if they give you more than one, look at it in this order: native, then SDS, then reducing. Native, then SDS, then reducing. Does that make sense? This is the majority of the lecture. Not because there's not many lab techniques, but because of my own deficiencies at teaching them. Isoelectric focusing is a gel electrophoresis method that separates proteins on the basis of the relative contents of acidic and basic residues. A polyacrylamide gel with a pH gradient, low pH on one side and high pH on the other, is used, right? Low pH on one side, high pH on the other. So this means that there's going to be a lot of OH minus over here, a lot of H plus over here, right? So that means this side's going to be negative and this side's going to be positive, right? Very good. When the proteins migrate through the gel, they will travel toward the anode until the area of the gel with the pH matches their isoelectric point. When a protein's at its pi, it has a net charge of 0 and will not be attracted. This is freaking insane. Insane. Proteins usually are what? Positive or negative? Overall. In general. Negative, positive, positive, negative. What are they? Neither. It's a hard question to answer. It's a hard question to answer because you don't really know what state you're looking in, right? You don't really know what state you're looking in, but here's the thing. Let's say that we had a bunch of proteins, correct? It depends. Yeah, it depends, right? DNA is what? DNA is what? In just flat out. Negative. Because of what? Phosphates. Very good. Phosphates. Good. Phosphate backbone. Okay, so let's say that we had a bunch of proteins and we dropped them. Let's make our own little grid. And this is pH 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? All the way up to here. I'll close the box. One sec. Okay. Let's say that we dropped a bunch of proteins. Let's just say. This is the positive terminal. This is the negative terminal, right? Let's say we took a bunch of proteins and we dropped them right here. We just weld them all up over here, right? They're obviously going to get protonated. Like the side chains are going to get protonated and they're going to be positive, correct? Since they're positive, they're going to start migrating to the negative terminal. And as they migrate, they're going to get deprotonated. They migrate, they get deprotonated, get deprotonated, get deprotonated, until they hit a point where all of their R groups are either protonated or deprotonated to a point where the charges cancel out. And do you see that at the point where the charges cancel out, it's no longer going to be attracted to the negative terminal. And it's also not going to be attracted to the positive terminal. It's just going to stop dead. The isoelectric point. The isoelectric point of the protein is where the R groups and the side chains and everything, right? All of it, the protonation, deprotonation of everything cancels out to zero charge. Zero charge. And since the charge is zero, it's not going to be attracted to the positive terminal, it's not going to be attracted to the negative terminal, and it's going to stop dead where it is. And it's going to stop dead in such a specific location that it's going to match up with the pH gradient that you made inside of there, and you'll be able to read the isoelectric point off of the ladder that you've created on the top. Does that make sense? This is really complicated. This is really, really complicated. Let's create a protein. Alanine, valine, histidine, aspartic acid, aspartic acid, aspartic acid, threonine, tyrosine, cysteine, or sorry, serine, cysteine. And then we'll have COO minus NH3 plus. Let's start out with everything protonated. This is going to have a +1. This is going to have a neutral. This is going to have a neutral. This is going to have a neutral. So the overall charge of this is +1. Okay? Right. Actually, sorry. We're starting off with everything protonated. So this is going to have a +2 charge, right? We put it over here, right here. Everything's protonated. It starts moving through the gel. As it moves through the gel, right, things start to get deprotonated. What's the first thing to get deprotonated? It's going to be this guy. This guy's gone, right? COO minus. That's the first thing that gets deprotonated. At around what? At around 2.2, it gets deprotonated. Now we're not at +2, we're at +1, right? As we keep going, one of these aspartic acids is going to get deprotonated. So it's going to go from 0 to -1. And this is now going to turn into 0. But is it going to move anymore? Is this protein going to move in an electric field? Is it? Is it going to move? Is it attracted to either direction? No. No, it's not going to move. So it's just going to stop dead wherever it was. And wherever it stops dead, that is the PI, because this is the Zwitter ion. What's a Zwitter ion? A Zwitter ion is something with multiple charges on it that has a net charge of 0. So the Zwitter ionic pH is known as the PI, the isoelectric point, and it will stop moving at its PI. It doesn't, guys, think about it this way. It doesn't matter what it is in the body. It doesn't matter what it looks like when it's inside you. It matters what it looks like at these pHs. What are you lost on? What do you not understand? Have you studied biochem yet? Okay. Then what are you not getting about the deprotonation? As the pH goes up, the R groups slowly get deprotonated. So they give me the pH and I should get the charges and see where it's at. So it's not that they get you the pH. You have a pH ladder across the field, across the actual isoelectric focusing like gel. And you're able to see where it stops and match up with that ladder and be like, okay, well, this stopped at this specific pH, so that's the PI of that protein. I didn't know entire proteins have a PI. Well, yeah, it's based, like Laura said, it's based on their R groups. R groups get deprotonated one by one until they settle at, yes, so R groups get deprotonated one by one until the charge of the whole protein is 0. In our case, it required one of the aspartic acids to be deprotonated and the carboxylic acid terminal. Can you do an example of a prop? No, I can't. There's no way I could think of something like that. I'm not smart enough. Okay. So if you guys are still a little bit confused, I urge that you ask more questions because I am open to answer them. Do you cut the protein before putting it through? No, you don't have to. So look, like they said at the end, let's just read the rest of this. When proteins migrate through the pH gradient gel, they will travel toward the anode until the area of the gel where the pH that matches their isoelectric point. When a protein is at its PI, it has a net charge of 0 and will not be attractive to the positively charged anode, so it will not move. Okay? So actually we load them up over here. It just doesn't make a difference. So everything, so we started the cathode. I was wrong about that. Everything's going to be deprotonated to start, and it's going to move towards the anode and slowly get protonated. let's do one more example. And we'll do a short example. We'll do a very short example, right? NH3, and we'll do leucine, lysine, arginine, histidine, aspartic acid, glycine, COO minus. And we'll go from everything being deprotonated. So lysine deprotonated is what? Completely deprotonated. Lysine completely deprotonated is actually negative because you have to remember it has an NH3 positive at the end. So NH3 is going to go to it's 0. My bad. 0. I was thinking of it from wrong one. 0. Arginine deprotonated. 0. Histidine deprotonated. 0. This deprotonated, -1. COO minus, and then NH2, which is 0 once again. Okay? This has a net charge of -2 when we load it up on this side. Since it's negative, it's going to start to get attracted this way, right? Does that make sense? So as it gets attracted this way, one of these things, it doesn't matter what, it literally does not matter what, one of these things is going to get protonated, which is going to make this a -1. And as we keep going, another one of them is going to get protonated, right? Which is going to make it 0. Once two things on this are protonated, we now have a 0 charge. It's going to stop dead wherever it is because a 0 charge can't be attracted to anything anymore. So that will tell you the PI of that. Does that make sense? It's going to attract toward the positive, right? And it's going to stop dead whenever it's been protonated enough. They will twist the question for sure. Yes, this is the AAMC we're talking about. How does the change in pH cause a change in protonation state? Okay, this is a question about acid and base basics. If something has a low pH, that means there's a lot of what? H+. So the H+ is going to hop onto the negative charges on that thing and protonate it. There we go. It clicked. I can tell when things click, and it clicked. Yes,
It's just typing out a hydroxide ion.
the concept isn't wild, but in practice, it's really complicated. Okay. All good? I'm going to keep going. Western blotting. Okay. This is a detection of a specific protein in a sample, right? So we have proteins that are loaded onto an SDS-PAGE, right? Gel, and they're separated based on size. Then the proteins from the gel are transferred into a polymer sheet and exposed to a radio-labeled antibody, right? One specific to the protein of interest, another radio-labeled antibody that binds to the first antibody, right? That's specific to our protein of interest. The polymer sheet is viewed using autoradiography. The protein of interest is bound to the radio-labeled antibody will be visible. Okay. Basically, you put some proteins on a gel. You want to identify a single one of them to see where it went. You put an antibody. Here's the protein. It has an antigen on it. I take this antibody that binds that antigen, and it binds, right? Protein, antigen, antibody. Now the antibody doesn't glow by itself. I have another antibody that binds that antibody and glows. Protein, antigen, antibody, anti-antibody. And this thing glows. And it tells you exactly where the protein is. That's what we're doing. Protein band detected by fluorescent emission of specific antibody. Boom, it's right there. We didn't know where it was before, but now we know, boom, it's right there. Cool? That's it. This is a good time to bring that up, actually. Snow, drop. How do you identify things? Southern blots are for DNA, northern blots are for RNA, western blots are for protein. Bro, antibodies are so annoying. Immunology in and of itself is so annoying. Like, what? You guys know about Graves' disease? You guys ever heard about Graves' disease? Right? What the hell do you mean that there's an antibody and instead of destroying the thyroid, the freaking antibody activates the thyroid? What? So look. It's an anti-TSH receptor antibody, right? So you would think that it destroys the TSH receptor. No, it activates it.
That's crazy.
What?
My sister-in-law just got diagnosed with Graves. And they misdiagnosed her, and it was wild.
It's the most common cause of hyperthyroidism in America, right? It's the most common cause of hyperthyroidism in America. But what do you mean the antibody activates the freaking thing? Antibodies are literally made to destroy. Oh God, the beef. It's beginning. Oh God, guys, brace yourselves. Okay. As an immunology major, I'm cooked. Yeah, you are cooked. Nah, there's no saving you on that one. I'm sorry. Okay. Next. Crazy things happening. Crazy things happening. Okay, Southern blot, same thing for DNA. Northern blot, same thing for RNA. We're not going over that. Okay, DNA sequencing. Really unimportant. Not going over this. Chromatography. Okay. Now we're doing interesting stuff. I want to change the color here. Cool. Now we're red. Red. Okay. Chromatography is to separate two things from a mixture, right? There's different types of chromatography, right? And it usually includes a stationary phase, which is typically polar, and a mobile phase, which is typically nonpolar. If reverse phase is specified, the properties of the two phases switch. So stationary phase is normally polar. Mobile is normally nonpolar. So for example, the one you did in college, right? Thin layer chromatography is on paper, cellulose paper, with hexane as a mobile phase. The cellulose is polar, and the hexane that you dip it in is nonpolar. And the hexane moves up the paper and brings up nonpolar stuff with it, right? Okay, now you need to know that like dissolves like. So hexanes do smell really good, but don't sniff them too much. If you have something that's super nonpolar, like this, it's gonna move with the nonpolar phase. And the nonpolar phase is normally the mobile phase, unless you have reverse phase. So if we have something like high pressure liquid chromatography, HPLC, this is gonna have a polar stationary phase and a nonpolar mobile phase. However, if we have RHPLC, which sometimes they won't even say reverse, they'll just say R. If we have RHPLC, we now have a polar what? Mobile phase. We now have a polar mobile phase. Does that make sense? Understood? Liquid chromatography. Silica is traditionally used as a stationary phase, while toluene or any other nonpolar liquid is used in the mobile phase. So here's how this works. You have a little vial. It's filled with silica. You have samples inside of here that you load up over here. You load it on top of the silica, and you pour toluene through it. And the toluene is going to pull some of the sample with it. And the thing that's going to elute first is what? The most nonpolar. The most nonpolar thing is going to elute first. Smaller or bigger? Small things. Why? Well, imagine that you're in a crowd of people. All of these are people. People. It's like a freaking protest, right? And you take a 5-year-old who's like 3.5 feet tall, and then you take some random 7-foot tall Yao Ming looking motherfucker, and you put them in the middle of this, and you say, go straight through these people. Who's going to have an easier time? The smaller dude. He's not going to get caught on anything. He's going to go through people's freaking legs. Yao Ming is going to get like hassled down and beaten the crap out of just because he's so tall. Right? Okay, cool. High pressure liquid chromatography. HPLC is a type of liquid chromatography that uses the high pressures to pass the solvent phase through a more finely ground stationary phase, which increases the interactions between the molecules in stationary phase, giving HPLC high resolving power. You have a container, you have a pressure generator, you have samples at the end of this, and you have a very fine powder inside of here. That's polar. You pressurize this toluene or hexane, and you slam all of that into this stationary phase, and you just punch it through, right? And whatever comes out first is whatever's least attracted to that and the smallest. So it's going to be the nonpolar, whatever comes with the solvent, and the smallest. I had a question that boiling it down asked if butanone or butanol would reach further in a TLC with a nonpolar mobile phase. How would you approach that question? Well, I would approach it with chemistry in mind. So here's butanone, and here's butanol. I'm assuming you mean 2-butanol, right? What's the difference? Nice chat GPT answer over there. What's the difference over here? Well, this thing has hydrogen bonding interactions, and it also has more polarity because of the fact that the oxygen is attached to hydrogen, which it has electronegativity with. This is going to have less of that interaction because of the fact that it doesn't bond to itself as much because of the decrease in the hydrogen bonding, and the fact that the oxygen is only bound to the carbon and not the hydrogen. Does that make sense? So this is actually going to follow the polar phase, and this is going to follow the nonpolar phase more. So this is going to come out faster. Does that make sense? What's resolving power? Just more power to do what chromatography does. I don't freaking know. Context clues, I guess. Okay. In reverse phase, HPLC stationary is nonpolar, mobile is polar. They really harp on that. And the reason they harp on that so much is because it comes up all the goddamn time. They literally just want you to mess up. They want you to mess up so bad. So make sure you read either reverse or R. Once you see reverse, your brain turns off, well, then just turn your freaking brain back on. And I would literally write it down, like on the notepad that they have, write it down. If you're doing a question about reverse phase, I want you to write it. You're going to be like stationary, mobile. What's the normal? Stationary is normally what? Polar. Now we're nonpolar. And mobile is normally nonpolar. Now we're polar. I want you to write it down. Literally write it down in front of you so your brain doesn't have to do freaking tricks trying to figure it out. Use the stuff that they give you to your advantage. Gas chromatography. Gas chromatography is gas liquid chromatography used to separate and analyze molecules that can be vaporized, right? Mobile phase is an inert or unreactive gas, such as helium or nitrogen, with stationary phase is a thin layer of liquid polymer that surrounds the walls of a tube. Stationary phase allows more polar molecules to elute slower, giving them a higher retention time. Make sense? I don't think we need to go over this. It's basically the same thing that we've seen before, just with gases. Good? Good. Awesome. Cool. Gas, gel filtration, size exclusion, right? Basically separate molecules by size rather than polarity. That's it. That's it. What graph? What graph? What are you talking about? This? This graph? No. No. Unnecessary. Why? We explained it so simply. Why would you want to confuse yourself? Don't look at the graph. The graph doesn't matter. What matters is understanding how all this works. Questions came up. So questions come up about this. About this? Okay, so hold on. The reason I don't want to explain this is because look how easy it becomes when I tell you how to explain this. This is the amount of time that has passed in the chromatograph, right? We have a mobile phase that is nonpolar, right? If the mobile phase is nonpolar, the first thing to come out is the most nonpolar. All they're saying is that this is the absorbance of that thing. Next thing that comes out, this is the absorbance. Next thing that comes out, this is the absorbance. Next thing that comes out, this is the absorbance. Right? That's it. That's all they're saying. So they're saying that the thing that's the most nonpolar has an absorbance of 0.2. But like, what does that matter to, like this is just what it looks like in a lab. So it doesn't really matter to us. One with the lowest retention time, the one that comes out the fastest. This one, 1. Highest retention time, 5. Yeah, that's it. It's very, very simple if you understand how chromatography actually works, which I hope you do now. Okay, ion exchange chromatography, right? We'll separate proteins by their net charge. Proteins, we're working with proteins here, by their net charge. The column is filled with charged beads, either positive or negative. In cation exchange, negatively charged beads are used, which attract positive proteins. Okay, listen. This always tripped me up. Every single time, this tripped me up, okay? So, negatively charged beads. Okay, wait, for size exclusion, small, no. Size exclusion excludes by size. So the fat people get left behind. Okay. So, in cation exchange, you're catching the cation. In anion exchange, you're catching the anion. What is a cation? A cation is a positive ion, and an anion is a negative ion, right? So, in cation exchange, you catch the cation. How do you catch it? You catch it with a negative. In anion exchange, you catch the anion. How do you catch it? You catch it with a positive. So in anion exchange, the beads are positively charged. In cation exchange, the beads are negatively charged. Does that make sense? So whatever gets caught, elutes later. Very cool. Next, affinity chromatography. Basically, you put a ligand in there or an antibody in there or something, and whatever sticks is going to come out later because it gets stuck inside that ligand. Does that make sense? Where'd Yasmin go? Someone go find her. Leave her. Yeah, I was like, it's so quiet right now. Okay, TLC. This is what we did in college. Cellulose, dip in hexanes. You put a bunch of your samples right here, and as the hexanes come up, they move up the plate, right? Make sense? This is the solvent front, right? Okay. And basically, the amount that the solvent front moves is Z. The amount that whatever moves is Y. So we want to ask ourselves, how much did this compound move based on the solvent front? That is going to be the RF. The greater the RF, the more like the solvent something is, because it's going to move faster. Have you ever seen questions about retention time? Sure. Maybe not phrased that way, but yeah, I have. Right? So the RF, the greater it is, the more it looks like the solvent. Because obviously the RF is a ratio between how fast the thing moved versus how fast the solvent moved. The closer it is to 1, the more it is like the solvent. So non-polar things are going to have a higher RF. Polar things are going to have a lesser RF. Oh, we were just wondering where you went. Understood.
My phone was having a stroke.
Also, guys, your phone's been weird today. Also, guys, if I am at all, ever, if I seem like I'm getting upset at the fact that you don't understand something that's not true, I'm just making sure that you understand what I'm saying, and I'm getting very stern in the way that I talk because it's what my mentor did to me. So I'm not upset with any of you if you don't understand something. I love all of you very much. It's just that this is something I'm very passionate about, and I love to teach it. And it's very, very, very serious to me. I want to make sure that you understand. Professor Malitsky. Shout out to Professor Malitsky, man. Okay. You guys know how distillation works? Y'all ever seen a distillation apparatus? Okay. Here's how simple distillation works. We got a flask. Boom. We got a sample in this flask. It goes up a column, comes down this condenser, comes out the bottom, falls into a flask of its own. Inside the condenser, we have water in this way, out that way. It cools down this whole thing. We put the fire right here. This thing boils, comes back down, boils, comes back down, boils, comes back down, boils, comes into here, cools down, condenses, comes out, boom, right there. And the way that this works is that you have a mixture of solutions. One of them boils at 25 degrees Celsius. One of them boils at 40 degrees Celsius. One of them boils at 110 degrees Celsius. One of them boils at 200 degrees. One of them boils at 105 degrees Celsius. So as this solution comes up to that temperature, things are going to start coming out. And you see that things come out in waves. Why do they come out in waves? This actually connects to what we talked about before. It's because of the fact that there's a layover time, right? There's a little bit of a layover time. And then you'll see stuff to start come out after this layover time. Correct? Does that make sense? So simple distillations are used for things that have a difference in boiling points 25 degrees Celsius or greater. A fractional distillation, I love Nile Red so much. A fractional distillation is a little more complicated. You have this long column. It's called what? What's it called in a fractional distillation? What's it called? What's it called? What's it called in a fractional distillation? What's it called? It's not called a condenser. No, it's not. You have a long column. It's not a fractal. It's not a fraction. It's called a fractionating column. Okay, Mr. Mandelbrot, fractal. Okay? It's called a fractionating column, right? And the fractionating column is full of what? It's full of aluminum foil. So there's more surface area for the gas to condense on. So what you'll see is that as the liquid begins to boil, let's say that you have something in here that's 100 degrees Celsius boiling point and 110 degrees Celsius boiling point. As something comes to 100 degrees Celsius, it reaches up, and obviously it's not 100 degrees Celsius up here, it's 80 degrees Celsius up here, but it's 100 right here. So the 100 is going to condense onto the 100 and fall back down. But then the next time it comes up, it's already warmed this part up. So now this part is 100 degrees Celsius. It's going to warm the next part up, but it's going to condense and transfer its heat and fall back down. And now this is 100 degrees Celsius. And then it's going to go up and it's going to warm this part up and fall back down because it transfers some of its energy. And then this becomes 100 degrees Celsius. And once this whole column is 100 degrees Celsius, then it'll start dripping out. However, now this thing is at 110, but it can't get out because all of this is at 100. So this 110, these molecules of 110 degrees Celsius vapor need to condense onto here and fall back down, and condense onto here and fall back down, and condense onto here and fall back down. Does that make sense? Does it make sense how each and every single part of the fractionated column needs to be warmed up individually before the liquid can make it out? And that's why it takes so long for it to come out. Fractional distillation takes a long damn time. I explained that so well, thank you. My teacher explained it well to me. So imagine every part of the fractionating column, like this with all the aluminum foil, section A, section B, section C, and section D. Each and every single one of them needs to be warmed up to the specific boiling point of your temperature before it has to come out. Does that make sense? And vacuum distillation. You want to speed up any boiling point of anything? Put it in a vacuum. Suck the pressure out of the chamber in order for something to boil quicker. Why? All right. We're talking about liquids that have these loose connections like this, right? But if there's pressure pressing down on the liquids, it actually pushes the liquid molecules together. In order to get a liquid to boil, what do we have to do? We need to get those liquid molecules to move away from one another. We need to get them to separate from one another so much that they move around, they leave, right? They leave one another. That's difficult when there's pressure pushing down on them, correct? If we alleviate that pressure, the liquid molecules no longer have a desire to be near one another, because when we alleviate that pressure, there's nothing pushing them onto one another. So they're already further apart. And if they're already further apart, it's easy to get them to boil and move even further apart. So the boiling point drops with a decrease in the pressure. Does that make sense? Understood? So if you want to drop the boiling point of something, take the pressure out of the vessel. Vapor pressure is interesting. Let's say you have a solution of hexanes and a solution of water. Here's hexanes, here's water. You put a cap on it. The boiling point of hexanes is very low. The boiling point of water is very high. Since the boiling point of hexanes is very low, it's possible that some of the molecules are already turning into vapor. And since there's more vapor inside of the flask that's exerting pressure on the top of the flask that has a high vapor pressure. Does that make sense? If you were in a vacuum, water would boil instantly? Yeah, it would, because there's nothing holding it together. PCR, I feel like I don't need to really explain this, but we'll walk through it. DNA strands and complementary DNA primers are heated to 95 for 15 seconds, right? So here's the target sequence. Add excess primers, right? And then here are the primers. So we cool so that the primers attach, and then we allow the enzymes to do their work to synthesize the new DNA. And then we restart. So the primers attach to this new DNA, and then we go again, and it doubles and it doubles and it doubles and it doubles and it doubles, and it goes on and on and on until we have billions of this DNA sequence that we want, just so that we can analyze it. SubhanAllah, that's so crazy. That's so wild to me. It's insane what we can do with science. Oh my god. Oh my god. Oh my god.
Can we just pretend it doesn't exist?
Oh my god. Bro, please.
Muhammad, why are you excited for NMR?
Bro, please. I can't. Oh my god. I forgot about this. No.
Gonna be honest.
Dude.
For the moment. That's why I joined.
Huh?
I waited for this moment, bro. It's like 8 a.m.
I can feel myself like sweating. like I can feel it. I need to take this off. Dude.
Yo, keep your clothes on.
Dude, I need a break. I need a break. Guys, I'm making an executive decision. Fuck all of y'all. I'm not teaching this. I'm not doing it. I'm not. I'm not doing it. I can't. Guys, I can't do it again. I can't go back. Y'all are on your own. You guys are totally on your own.
The OChem tutor on YouTube has a great video.
I'm sure he does. And you know what? You know what?
We don't need to do this. We really don't.
You know what? He's a better man than I am.
He's a better human being. Nobody wants to deal with spectroscopy.
Yeah, exactly. All right. Audio radiography. So, what's up?
Nothing, go.
Audio radiography is used to identify radiolabeled atoms. We talked about it before. It's basically like the fluorescence thing. Samuel will teach it. Yo, Sammy's the GOAT. What? Did she actually say that? Sammy's going to teach it?
NMR?
Yeah.
I mean, I could.
She hates it too. I can hear it in her voice. I hate it.
Listen, Sammy, I'm going to tell you one thing. As someone who's been doing this for 2 years now, and also I've been tutoring for the MCAT for 3 and I tutored for the MCAT. The first time I tutored for the MCAT was 2 days after I got my score, by the way. Right? So I've been tutoring for the MCAT for 3.5 years now. Never do something you don't like doing, even if you know it well.
No, it's not that I don't like it. It's not that. I mean, the last time that I thoroughly studied it was probably like 2 months ago.
Oh, bro, you'll be fine. The last time I studied NMR was I was probably 7. Okay. So, Samia, chapter 8 and NMR are now on you.
Okay.
Have fun. Okay.
Yeah, get out of here. Go deal with Vidig and Grignard.
Yo, the Vidig and Grignard were lit.
They were so much fun. I don't
lit.
get paid.
No,
Okay.
I'm gonna crash out. Like I'm gonna fail this exam.
You'll be
okay.
You'll be
You're
fine.
not gonna fail, inshallah. You're gonna be fine.
You'll be fine. So let me tell you how many questions I've gotten about this. 0. Let me tell you how many questions I've gotten about this. 0. Let me tell you how many questions I got about this. 0. All right. So That tells you how much we're going to do about them. Radio immunoassay. Okay, this is kind of like, do you guys see what's at the bottom of the screen right now? I'm scrolling back up.
Can you scroll up? Thank you.
I'm scrolling back up. Okay. Radio immunoassay. Similar to ELISA, the wells of the plate are coated with primarily antibodies specific to the protein, right? Then radiolabeled protein containing tyrosine residue with I-125 out of the wells binds the antibody, right? Then the concentration of the radiolabeled protein is determined by counting the gamma emission. Then a sample of the protein of interest is unknown in an unknown concentration out of the wells, where it competes for the active site of the primary antibody, displacing an amount of the radiolabeled protein. The concentration of the radiolabeled protein is determined again by counting the gamma emission. Difference in concentration provides the concentration of the protein of interest. Okay, here's what they're saying. You have an antibody that allows this protein to glow. You count the glow, right? You count the glow. After you count the glow, you add a protein that's going to kick some of this off, and you want to know the concentration. It kicks it off, and you count the decrease in the glow. By the decrease in the glow, you know how much of it bound. You know how much of the new protein bound, and now you know the concentration. That's it. Make sense? Okay. Mass spec. There's one thing. There's only one thing that I can teach you about mass spec, right? There's one thing that I can teach you about mass spec, and it's this right here. M+1, right? M+1. That's it. When you look for the M+1 peak, you're going to understand how the mass spectroscopy works. Because there's going to be one intensity for the mass, and there's going to be one for the M+1. That's it. And if you're able to figure that out, you can figure it out on the MCAT. I know that's very vague, but that's how I got past mass spec on the MCAT. As long as you can look at the primary mass of the thing and the M+1 spike, you'll figure it out. I don't know how you'll do it. I don't know how I did it, but I did. I'm not good enough at teaching these things, and I'm okay with admitting that. ELISA. ELISA, I had never really gotten questions about it, to be honest. You don't need to know it. This is just another antibody thing. Admin degradation legitimately never, ever, ever came up except for in Orgo 2. Gram staining, guys, what color are gram-negative bacteria? Pink. What color are gram-positive bacteria? Purple. Very good. That's all you need to know. And oh, wait, why?
Peptidoglycan wall.
Peptidoglycan. So what color is the gram stain? Right? So if something has a thick peptidoglycan, which one has a thick peptidoglycan wall? So basically what I'm saying is if you have gram positive and you have gram negative, what you're saying is it's positive for the wall and it's a negative for the wall. So gram positive has a thick peptidoglycan wall and stains violet. Gram negative has a thin peptidoglycan wall and stains pink. But what does gram negative have that gram positive doesn't? Do you guys know? 3 letters. 3 letters. It's something I'm looking for. Not lipodocoic acid. No. I'm looking for a very specific thing. I bring it up in every lecture because it's important to medical school. Lipopolysaccharide. Lipopolysaccharide, because lipopolysaccharide is wildly inflammatory. It's really, really, really inflammatory. Oh my God, it's 1:16 in the morning. Ooh. Okay, dude, I've legitimately never heard of this in my entire life. I don't know what the hell this is. I don't. So we're not doing it. Do you guys see how, I don't know why I was avoiding doing this lecture for so long. Like half of it is just me saying I'm not teaching. Salting out in dialysis, right? Adding salt to a solution containing proteins can allow it to selectively precipitate out the proteins. Salting out is due to the competition between salt ions and proteins for water to keep the protein solution. The salt concentration at which a protein will precipitate varies for each protein, right? So basically, we increase the concentration until the protein comes out of solution, right? Does that make sense? Yes? No? Yes, no? Maybe? Yes, no? Okay. protein is aqueous. I increase the concentration of the salt outside to draw out the water. Look, here's the protein in here with a bunch of salt. I put salt in here. It draws out the water. As the water decreases, the concentration of the protein goes up. It goes up until it's no longer soluble. It precipitates out. Does that make sense? It doesn't turn into salt, it turns into protein. How would a protein turn to salt? 25 hours. Okay. Assalamu alaikum, Muhammad. See you later. How would it increase the guys, look. You have a container. This container has a set volume of water in it, and it has protein dissolved in this water. I put salt outside. The salt draws out the water. Molarity equals moles over liters. I'm decreasing the liters. Does the molarity go up? If the molarity goes up, things precipitate out. Because they're not soluble past a specific amount of moles inside of that amount of water. Make sense? Yes? Yes, no? Good. Okay, now we're all on the same page. Very good. Good. Oh, my favorite tests. Reducing sugar tests. Okay. I have a sugar. What is this carbon called? Anomeric. Very good. The anomeric carbon is bound to this oxygen and also has an OH. Because of that, this H right here is very labile to be taken. It's very labile, right? It can be taken very easily. Since it can be taken very easily, what's it called if you take the hydrogen? What's it called? Are you oxidizing or reducing? Oxidizing. You put silver, Ag+. It steals the electrons of the hydrogen, right? And that leaves you with what? That leaves you with this. What is this? What is it called? What's it called? Not a reducing sugar. This is a reduced sugar. Okay, yes. Or sorry, no, not a reduced sugar, an oxidized sugar. This is an oxidized sugar. We reduced the silver, which is why this is called a reducing sugar. There's a sugar that reduced the silver. But what is this called? This is an oxidized sugar, which is called a lactone. Very good. A cyclic ester. Because look, this is COOR. This, in a cycle, is called a lactone. Yeah, honestly, goated. Good for you. MashaAllah. It's called a lactone, okay? Any sugar that has an OH attached to the anomeric carbon is a reducing sugar. Your question right now is, when would it not? Well, let me give you an example. Oh God, I'm rusty. Come on, man. Is that a reducing sugar? No, it's not. There's the anomeric carbon. There's the anomeric carbon. Where are the OHs? Both the anomeric carbons are involved in the bond between the sugars, meaning it's no longer reducing. And like Laura said, this is an alpha 1,6 bond between two glucose molecules. Sorry, not 1,6, 1,1. My bad. You're correct. 1,1. 1,6 would be up to the 6 carbon. You're good. But, however, let me show you something. Oh, sorry, sinusitis. All the time. All the time. Anytime the weather changes, I get sinusitis. How about this? Typhoid Mary. 1-4. Is this a reducing sugar? Yeah, it is. The quick way to do this is look for the oxygen in the ring. The oxygen in the ring, the anomeric carbon should be right here. Oxygen in the ring, the anomeric carbon is right here. There's your OH attached to the anomeric carbon. Oxygen in the ring, oxygen in the ring. Anomeric carbon, no OHs. Non-reducing, reducing. And what does the reducing reaction look like? It's really cool. It's really, really cool. You have a flask, you have a sugar, you pour silver into the flask, silver chloride, and the silver coats the flask, and you get what's called a silver mirror effect. You guys should go into YouTube and look up silver mirror reactions. Very, very cool. I really like it. It's one of my favorite reactions in chemistry. And all these sort of work the same way. I don't think you need to know the difference between all of them. cDNA libraries. Okay. cDNA libraries. Where to start? And I'm legitimately asking because I have no idea what they are. I have absolutely, in the beginning, I have no idea what cDNA libraries are. And I'm okay with that. Got me a 521 on the MCAT. So, you know. Back to NMR. Hell no. Okay. I think that'll be it for lab techniques. Thank you guys so much for watching. Please consider supporting the channel. Check out the links in the description below for everything associated with the channel and to keep up to date with everything that we do. I love you guys. Thank you so much. And I'll see you in the next one. Zoom chat, hang out.